Hi everyone, welcome back to the channel. Today we'll continue on our oscillator series. So in the last video, we took our oscillator and we added an inductor to it, and we did the layout of the inductor in HFSS. We tuned it a little bit, and we brought the layout from HFSS to Cadence. And then at the end of the video, I kind of showed you how you can replace the layout in Cadence with your own layout, as long as you can, get the entire layout on grid, right? I showed you how you do that on grid. So I went ahead and did the whole thing. In the earlier video, I just showed you one section, but here I did it for the whole thing. So you can see that in M11 is where we have our actual inductor. Then M10 is the transitions. And M8, we have our center tap, right? And that goes out here and it kind of ends in the ground here. In reality, of course, you have to bias this separately, but biasing we'll cover in a separate video. And I made the walls using these M1, M11 grids. Go into this. So this is the M1, M11 5x5 grid. And these grids come from a previous video that we discussed on this channel. So let me just quickly go through that, which is this one. So metal grids and layout blocks. So in this video, you should have watched the introduction to layouts. You should have watched the DRC, LBS, and PEX in this process, the GPDK process, and also this metal grids, if you haven't done that. And I uploaded the GDS file of the metal grids already, just as a refresher, in layout blocks v1. Okay, and obviously it's a continuation of the class coupled VCO design series, so you should have watched the previous videos on this, and we'll build on these. Okay, so in this video, what we'll do is we'll do the actual layout of the entire oscillator and simulate, do verification, DRC, LBS, and PEX, extract the parasitics, and see what the difference is at the end. Right, so that kind of concludes this this design. So let's go ahead and do that. Okay, so I'll just make a copy of this library. Call it A08 VCO layout for YouTube. Okay. All right, so this is kind of where we had stopped. So I'm going to make a few changes to this design before we move on to the layouts. Okay, so the main change, let me actually do the maybe let's run a quick simulation just to check if that's working. Because this is what we had, right? 0 volts, it was 10.24, and it could phase noise performance at around 1 megahertz, offset is -100, and the form is 183. Okay, great. So we can close this for now. So a few changes we need to make before we do the final layout. So the first thing is that I noticed these resistors were ideal, so we'll replace them with resistors from the PDK. So we go into resistors and we'll use the diffusion region resistor. Okay, so I'll place one here. I'm going to make this 15 microns to get the 1K. And then we can place it in. And we can label this to be okay, and then we have one more. So that's the first big change. That shouldn't make any difference to the circuit itself. The second major one is that we need to flip these varactors. The reason we need to flip them is that when we do the layouts, the body contact of this MOSFET, this MOS cap, I guess, needs to be grounded. And that's because the body is shared between all transistors on the chip, at least in this process. So in some processes, you have like an isolated body, and in that case, you can have a separate voltage for the body. But for these MOS caps, at least the body is shared. So if you try to do it this way and do LVS, it'll give you an error saying that this body is grounded, but this body is not grounded. It's connected to some voltage. So let's fix that. It looks like it's kind of DC grounded, but that's not what I mean. I mean, it has to be actually connected directly to ground. Okay, so how do we fix that? Out, and then we'll flip that back. Okay, and then we'll move the ground out here. We'll use this guy. Okay, so now it's the same thing. It's the same voltage applied across this reactor, but the body is now grounded directly, right? So this is a better orientation, and this will help us clean the LVS errors that will show up. Okay, so these are the major changes. So what we can do is try to run the simulation and see what we get. It shouldn't be that different. Haven't really changed much. Okay, so it's slightly better, which is a nice thing. Okay, the next thing we need to do is that since I've already done the layouts, I know sort of what the issues will be. Is that once you do layout and do parasitic extraction, we need to actually tune these capacitors a little bit so that we get the right value, right, for the range. We want it to be from around 9.7 to 10.3. So since I've already done it, let me actually just go ahead and do that beforehand itself. So in this case, the width we chose was 1 micron and 55 multiplier factor. The layout becomes weird when you do that because it becomes too thin and then a lot of them. Instead, what we can do is we can make the length 5 microns, the width 1 micron, and the multiplier factor to be 50. Right, so it should be actually 11. So 11 times 5 is 55, which is what we had here, which is 55 from here. But I increased it a little bit because as we'll see that when you do the layouts, it will shift the actual capacitance value down. The reason it actually you need a slightly larger here because when we do the layout, we'll kind of join these capacitors end to end. When you join them end to end, the fringing capacitance kind of disappears. Because the fringing cap disappears, the actual capacitance value drops a little bit. So you need to make it slightly larger to get the same results. Okay, we'll also replace these guys. These are all the same size. So number of fingers is 20, right? This one and this one both are 20. And the channel size is 500 nanometers. Okay. And these guys, finger width was, I believe, 2 microns. Number of fingers we chose 100, but this 90 to be slightly better when I was tuning it. So it's slightly different than what we had earlier. And lastly, it's this guy again. We have to choose a value slightly larger than what we've done here. So the width, where is it? So it's 5 by 50, right? So width is 5, length is 1, and we have 50 of them. Instead, what I did is I made the width 5 and the length 5. So then we need only 10 of them. But since we have to decrease it a little bit, I'm going to use 50. Right, so 5 by 5 by 15 is larger than sort of what we had earlier, which is 5 by 1 by 50. Right? Okay, so that tuning you can do on your own, but since I've done it, I know the values, and that's why I'm doing it like that. Okay, let's simulate this and see what we get. Okay, it's 10.7 at the higher end. And make this 800 milli. To around 10. So actually I made a mistake in what I said earlier. I said the fringing capacitance decreases. It's the other way around. When you have the layout, when you do the layouts, the fringing cap kind of increases, right? You have parasitics added in. That's why, because of those parasitics, we'll see that this actually shifts down a little bit. So right now it's going from 10 to 10.7. We want to bring it down from 9.6, 9.7 to 10.3. Right? So once you do the layout, because of the added parasitics, this will actually shift down a little bit. Okay, so enough of that. Let's go ahead and actually do some layouts. One last thing is we need to make a cell out of this, right? So let me quickly do that. Save this, save. Okay, so where are we right now? We are here. This is what we save. So I'll make a copy of this. Call it cell. Make another copy and call that test bench. Okay, great. So, okay, let's open up the cell first. We need to delete all these sources. We can delete these guys. We can delete this. Delete these. Delete all of these grounds. So delete these things. Set up some pins. X, Y, GD. Actor voltage and tail voltage. X, Y. Actor. And then we have many grounds. Put them. That's ground. That's this one. This one. Right? So I think that's pretty much it. All right. So let's create our box. Say X, Y. Okay. We have a cell view, we have a schematic. Next thing is to do the layout. So we need to create a new cell. Library 7 VCO cell, and we want layout view, layout Excel. Okay, yeah, that's good. So if you click this, it will create from the source file all the components that we have. Yeah, all of these guys, but these are not the right values. We need to change the values and then connect them all up. So since I've already done one video on how to do layouts, I'm not going to do the whole layout in front of you, otherwise that would take forever. Instead, you can kind of just download the layout from here, the GTS file, and import it and look at what I've done, or you can do your own layout. The layout that I did was kind of very very quick. I didn't think too much about different factors. At these frequencies, it's okay to be a little bit careless, but at higher frequencies, maybe you have to try several different layouts, and then you have to be a little bit more mindful of how you're kind of doing cross connections and things like that. But this is just an example, I guess. It's not a real tape out, so you can just go ahead and use the layout that I've done or do your own layout. So let me pause here and copy that layout here, and then we'll continue from there instead of having to connect everything myself. So I'll delete all of these and I'll do that. Okay, so this is what the layout looks like. If you download the GDS that I've uploaded, you'll also see the inductor in here, which I've removed in this case, but you can easily add that, right? That's the inductor. So when you download it, it should look something like this. Okay. The one that I have there actually is slightly different than this. But yeah, anyways. So this is the actual layout of our structure. So if you compare it to the schematic, you'll see that this is the tail transistor. These are the two cross-coupled transistors. We have our cross coupling here. Goes like this, comes down like this, goes like this, comes down like this. And then we have the different caps. So these are the two MIM caps, and these are the other two MIM caps. These are the MOS caps. Right, so you can go through the details. These are the two resistors, and see what I've done here. I'm going to skip all that, and then we'll go forward to the verification, since you already have the GDS file available to you. Okay, I've already done a video on DRC, LVS, and PEX and how to set this up correctly. You can watch that video. But once you set it up, you can essentially just submit. And since I've already done this before, I kind of cleared the DRC errors, as far as I remember at least. Hopefully there are no new ones. Yeah, so we have a clean DRC. And you can watch the video on DRC if you don't know how to do that. But clean DRC, and then we'll run LVS. Again, I've already covered this, so I'm not going to do it again. Let's make sure that the LVS is good. Very nice, very clean, right? Okay, so we can now extract the parasitics. I've gone through these settings already earlier, so I'll just quickly go ahead and set it up. This one is called A08 VCO layout. And the cell is, what's the cell? It's this one, right? A07 CCVCO, A07 CCVCO cell. And we can say the extracted V1. Okay, override. So once it's done, we'll continue. Okay, so this is done. Let's go ahead and take a look at it. So I'm going to close this. I'll close this as well. Go to test bench and we'll set up a test bench. Okay, so let me move this one out. This one out as well. We can delete all of this. And we should include our symbol here. Okay, great. Pick it up. Okay. This is the tail source bias. And this is the reactor bias. And our ground. All right. And this was our schematic, right? Okay. Let's go ahead and okay. So to actually check the parasitic extracted results, we need to set up a new environment. And this is also something I've covered in the previous video on LVS specs and DRC. So we need a new cell view. And this should be for the test bench. Test bench. LC VCO test bench, config. Okay. Schematic view, use template, go down to Spectre, okay, and hit okay. 7cc VCO test bench. Yeah, so the config appears there. All right, so you can sync it up and then go to setup, design, say config it, okay. Refresh a few things and then sync it again. Okay, now let's test it. So what we need to do is we need to change this view from the cell view to our extracted view. Sync it up and then we'll run the simulation and see what happens. It will take a few minutes. An error, so I forgot to label these. XY. Yeah, so that the pulse can be applied right for the startup condition. Okay, let's run it again. Okay, simulation is done. You can see that at 800 milli, we are at 9.65, so it has dropped quite a bit from 9.99 or so. But the phase noise is good, and the swing is a little bit lower, but that's okay. Again, because of the parasitics. Okay, so let's also check the other end of the band and see what we get. And once it's done, we'll continue. Okay, so you can see it's going up to 10.25, so 9.65 was it to 10.25, and that's a pretty good range. That's kind of covers the range that we wanted to do. We want to over optimize it at this stage just because we may need to make changes to it in the future. Okay, so we have a nice layout now. We've done parasitic extraction, we've simulated the inductor separately, and we've added that to the simulation using this file. So what is really left, right? There are two things that we need to still look at. What are those things? So in the layout here, if you take a look, we have connected the inductor out here. But in HFSS, if you remember, we placed a port on that inductor, right? So that port actually adds a small amount of parasitic inductance in HFSS to this node. And secondly, if you actually pay close attention, where I placed the pins for this X and Y is not exactly at this location. I placed the pins, somewhere else. I don't even remember where I placed them. Let me see. It's somewhere here, I think. Yeah. The pins are here for X and Y. This is not exactly correct. You need to place the pins even in cadence out here. And we'll see that that can have an impact as well. So we'll correct the pin locations. We'll also remove that parasitic inductance that comes from the ports, the lumped ports in HFSS. And we really need to discuss how to properly transition from HFSS to cadence in this kind of co-design environment. So that's the next thing we'll discuss. Maybe not in the next video, but in the future videos. And another thing we need to discuss is how do you actually match, right? So right now, this doesn't have any load impedance. It's kind of open circuit. But we need to find out, suppose this is connected to a next stage, let's say a power amplifier or a frequency doubler. How do you match it to the next stage, right? So since it's an oscillator, we'll do a load pull and we'll see how to do that correctly and also include matching networks to the next stage. So hopefully you're excited about all that. Hopefully you kind of enjoyed this video. I highly encourage you to do your own layout, clear your own DRC errors rather than just using the same layout that I've done. This is probably not the best way to do this layout, but it's up to you to do that. So if you have any questions or comments, leave them on the comment section below. If not, I'll see you in the next one. Thank you.